Everyone, in this video we'll take a deeper dive on the concept of an autocovariance, in particular the assumption of a constant autocovariance. So in the last video, if you watched it, we discussed that there are three things. Okay, so under stationarity, okay, so in order for a series to be considered stationary, in this case weakly stationary, okay, it needed to have three properties. The first of which is that it needed to have a constant mean. Okay, a constant mean. And this suggested that the expected value of the time series variable at any point in time is just a constant value, say mu. Secondly, it also suggested that that time series variable should have a constant variance. So it suggests that the expected value of the square differences, okay, from the mean, so that's yt minus mu, should be also constant, okay, equal to some parameter, say sigma squared. And the third assumption is that it has a constant autocovariance. And that means that, so mathematically, we write this as the expected value of yt1 minus mu, yt2 minus mu is equal to gamma t2 minus t1 for all t1, t2. So let's try and break down what that means. Okay, so for the case of a weakly stationary time series data set, an autocovariance is basically, okay, how y relates to its past values. Okay, so how it relates to its past values. So let's analyze this form here. So for example, mathematically we said it looks something like this: yt1 minus mu, yt2 minus mu. So this is one time period, this is another time period. Say this is the present, so t2 is the present, this is the past. Essentially, we're getting a sort of covariance between the relationship of the present and the past. Okay, so to be a bit more general, okay, it looks something like this. We're trying to get the expected value of yt minus the expected value of yt, okay, times yt minus s, or its past value, okay, minus expected value yt minus s. And this is equal to some gamma s, wherein the s could be equal to 0, 1, 2, and so on. Now, as I said in the last video, okay, if a series has a constant mean, so if it satisfies 1, say 1 suggests a constant mean, it means that the expected value of y sub t is equal to mu. But we say that it has a constant mean for all time periods, so it should extend into the fact that any time period, whether t plus s, okay, that's equal to mu, or expected value yt minus s, that's equal to mu, because the mean doesn't change for whatever value of yt it is. So this here is just mu, and this here is also mu. So again, we said our equation reduces to expected value yt minus mu times yt minus s minus mu. Okay, so a special case, so let's say when s is equal to 0, so when s is equal to 0, so the equation will reduce to expected value yt minus mu, okay, then this is yt minus 0, since s is equal to 0, minus mu. And you're gonna be left with expected value yt minus mu times yt minus mu. But you actually know this value here, okay, and that's actually just sigma squared, which is our second assumption here. okay? And that's actually equal to gamma 0, or the autocovariance at lag 0. So at the 0th lag, or at the initial time period, it's the autocovariance is just equal to the variance itself, okay? But as you go along in subsequent lags, that this will change. So say for example, when s is equal to say 1, okay, so expected value yt minus mu times yt minus 1 minus mu, well, this is gonna be equal to gamma, okay, this is gamma 1, or the autocovariance at lag 1. So this is a present value, and this is some past value. And all that assumption of constant autocovariance is trying to push is that autocovariance, whether you do it at, say, lag 1, lag 2, lag 3, lag 4, whatever lag, there is some sort of constant trend that you see in the autocovariances that you will end up computing. So just to review, in order for a series to be weakly stationary, it needs to have a constant mean such that the expected value of the series variable yt is constant across the entire series. It needs to have a constant covariance, and as we just recently discussed, it needs to have a constant